Okay, so please click continue if you get a notice about the recording. Okay, great. So welcome everybody to today's discrete optimization talk, not talks, because we only have one of them. We're happy to have Jannis Kurtz with us today as our speaker. Jannis did his PhD at TU Dortmund and was then a postdoc at the Aachen University. And he's now a visiting professor at the University of Siegen. And Jannis has worked primarily in robust optimization, robust combinatorial optimization, and compressed sensing. He's going to tell us about some recent work in that space today. So Jannis, please go ahead.
Yes, hello everybody, and yeah, thanks to the organizers for giving me the opportunity to give a talk in this nice seminar. So I want to talk about group model selection in compressed sensing, and this is joint work with Boubacar Bar from Cape Town and Oliver Schaut, who was with me in Aachen at this time and who is now at ZF company. Yeah, maybe for the introduction, what's the framework of compressed sensing? So the classical framework is you have a very high dimensional vector X. This is your signal, which you don't know, which you want to know. And then you have a measurement matrix A, which you apply to your vector X. And this measurement matrix has M rows, which is much smaller than the dimension of the signal. So what comes out here is a measurement vector Y, which is has a much smaller dimension than your true signal. And now the main task is, so the only thing you know is the measurement and your measurement matrix. And you want to recover your true signal X. So without any assumption, this is not possible since you have an underdetermined system. So you have infinitely many solutions X, and it's impossible to recover the true signal which you measured. But there are, if you have further assumptions, then this is possible. So the classical assumption is, so you have applications where your signal is sparse. So most of the entries are 0, and only some entries are non-zero. So there are different kinds of sparseness. We will consider group sparsity. I will show you on the next slide what we mean by this. And then you want to have measurement matrix A, which is information preserving. So what you want is that the information from X goes over to your measurement vector Y. So you need some information so otherwise you cannot recover X. And then you want to have a recovery algorithm which is tractable. So giving your measurements in the matrix, recover the true signal efficiently. And so what we consider in our work is not the classical sparsity, but we consider group sparsity. So in this case, you have a signal of dimension n, the true signal. And what we assume is we have a set of groups, so we have m groups, and each group is a subset of indices in these indices from 1 to n. And now we assume that our true signal is G group sparse, and G group sparse means the support of the signal is contained in at most G of these groups. So G is a given parameter. And you assume that the non-zero entries of X are contained in G of these groups. So you can consider a signal like this. So the groups are given in advance. It can be any structure of groups. So in this case, for example, you could see here's one group of indices here, here, and here. So there's some noise which you want to get rid of. But you can assume here that your signal is 4 group sparse. So the non-zero entries are contained in at most 4 groups. And there are many applications in image processing or genetics where you can assume that your true signal is group sparse.
So Jannis, a quick question. So the set of groups is provided based on the application domain?
Yes, the application depending. This is depending on the application.
And
so,
is it usually is capital M usually very large?
yeah, it depends. So I mean, so normally you would. So what you can do is you can consider groups which are these from a block structure. So you have intervals of indices, and then you would shift the interval by maybe one point or more. So yeah, depending, if you have groups like this, then you would have n groups.
Sure.
So yeah, it depends a lot on the application, I would say.
Okay, thanks.
Good. And so what we want is, as I said, a matrix A which is information preserving. So there are a lot of conditions on this in the compressed sensing literature, and the one which I want to concentrate on here is the RIP, so the restricted isometry property. And basically this property says that, so you have a small value delta k here, should be small, and now you want to have this condition to be fulfilled for all k-sparse vectors x. And basically this condition says if you apply your true signal to your measurement matrix, then the norm doesn't change much compared to the norm of your true signal. So if this delta is small, then this is very close to each other. So what you want is that the norm, the norm of x goes over to the norm of y somehow. So you don't lose this information at least. And now the question is, how do you construct matrices which have this property? And there's a very nice result which says you just have to pick random Gaussian matrices. So each entry is drawn from a Gaussian distribution, and you normalize your matrix, and then you have the RIP with high probability if you choose enough rows. So the number of your rows, so the number of measurements in the end has to be of order k times log n divided by k. This is a basic result from compressed sensing. So k here is the classical sparsity. So I will show you a similar result for the group sparsity. So in fact, what you have to do is just draw a random Gaussian matrix with enough rows, and then with high probability you have this condition. Now you want to have an algorithm, and there are several algorithms or several approaches to recover the signal. And one which we considered is the iterative hard thresholding. In this case, it's the more general variant for model-based. So the model-based iterative hard thresholding. In this case, you can apply it directly to group models. And the idea is basically to do a projected gradient descent on this objective function, so on the least squares. So then your negative gradient is given like this. And the algorithm is very simple. So it's just, you start with a 0 vector, and then you do basically gradient descent. And in each iteration, you have to project back on your true support. So the PG here is the projection problem, which takes the vector u and finds the closest G group sparse vector to u. So what comes out here doesn't have to be G group sparse, but what you do in each iteration, you project on a vector which is G group sparse. And there is also, for this algorithm, there's a nice result that you, so if A has the RIP, then also this converges. And in if you have, if you consider group models, then the number of measurements you need to so that the matrix has this property is of order G times G max plus log M. So M was the number of groups. G max here is the maximum group size, and G is the number of groups you can select. So if you again draw a random Gaussian matrix with enough rows, then this algorithm converges to the true signal X. So the signal which you calculate here is your true signal which is unique in this case. Good, and now the main question, or the main problem which we considered in our paper is this projection problem. Since the algorithm is very easy, so here you have to do some matrix calculations, but the big problem is the projection problem here. So how do you solve this? And Baldassar et al. Already showed in 2015 that this problem is NP hard, and actually it's exactly the weighted maximum coverage problem. So you can easily see that by these 3 steps. So if you consider, so you want to minimize this norm, so you try to find the closest G group sparse vector. Now the only constraint we have here is considering the support of Z. So we can choose the entries of Z as we want. So we will always choose them equal to the entries of U if we are allowed to set the entry non-equal to 0. So everything vanishes here except the entries of U which are not in the support of Z. So what you do here is you minimize the entries of U in this norm which are not in the support of Z over all G group sparse vectors Z. And now this is equivalent to maximizing all entries which are in the support. So the objective value here is not the same. So this can be different to this one, but what I write here is the argmin and the argmax. So the optimizer here and here is the same. So the one which minimizes what's not covered by Z maximizes what's covered by Z. And yeah, if you write this, if you write out the 2 norm, then it's just the given. So you sum up the squared entries of U which are contained in the support of Z. So in fact, this is exactly the maximum weight coverage problem. So the maximum weight coverage problem has given n weights, which are in this case the weights of U, the squared weight, the squared entries of U. And you have given a set of groups, of indice groups, and again a parameter G. And what you have to do is select G groups such that the sum of all weights in these groups are maximized. So this is exactly what I showed you on the last slide. So yeah, basically what we solve here in each iteration of the gradient descent is a maximum weight coverage problem. And Baldassar et al. Could show that you can solve this problem in polynomial time if you consider group models where the intersection graph has no cycles. So what the intersection graph is given here by an easy example. So the intersection graph has nodes for each group and an edge if the groups intersect. So very easy graph. And if this graph has no cycles, then you can solve the maximum weight coverage problem or this projection problem in polynomial time by dynamic programming. And now what we could show is a more general theorem. So what we consider instead of the intersection graph is the incidence graph. So the incidence graph has a node for each group, but additionally a node for each item. And now we have edges only between items and groups if the item is contained in the group. Also very easy construction. And we could show that, again, by dynamic programming, that is the tree width. I don't want to go in detail what this is. So it's somehow this the tree structure of the graph. So if the tree width is WT, then you can solve the problem in this runtime. And so if you fix, especially if you fix the tree width, then this is also a polynomial time algorithm. And it generalizes the result of Baldassar, since what they consider, so you have this easy inequality that the tree width of the incidence graph, the one we considered, is lower equal to the tree width of the intersection graph plus 1. So, and they consider intersection graphs without cycles, so it's a tree or a forest. So this has tree width 1. So basically what they consider is graphs which have where the incidence graph, or they consider group models where the incidence graph has tree width at most 2. And now our result also holds for larger tree widths. So we can fix the tree width to 5, for example, then everything here is constant and we have a polynomial algorithm.
Jannis, does your algorithm have the same runtime for the smaller class of graphs that is considered in the previous paper?
No, so our construction is different. Mm-hmm. Very very hard to show. It's very technical. So they have m to the power of 2 times g, and we have an m times n times g squared here. So yeah, it's different.
Okay, so if you have a graph that's satisfies the assumptions of that previous work, then it's probably faster to use that algorithm.
Yeah, and easier to implement.
Yeah, okay, sure.
Good. So additionally, we showed that so we have a class of group models now which can be solved in polynomial time. So basically, if the tree width is bounded, and we showed that the problem is NP-hard, even if you consider incidence graphs which are grid graphs and have only the weights have only values 0 or 1. So you can consider a graph like this. So the squares are the groups, the circles are the items. So if you have a grid graph like this, this class of graphs is so the maximum weight coverage problem is NP-hard for this class of graph, and you would obtain this from the compressed sensing point of view if you have a picture with pixel values which are only 0 or 1, so black or white. And your groups are 2 times 2 pixel windows, which you shift over your picture. Then you would obtain graphs with this structure. So already this problem is NP-hard. So anyway, we want to solve the problem, not only for the case where it's polynomially solvable. So what we could derive easily, or even Baldassar in this paper already derived this, is an IP formulation. So you have here y variables which are 0 or 1. So for each group you have one y variable which is 1 if you select the group, or 0 if not. So you have this constraint, you can select at most g of the groups, and then you have z variables for each item. And additionally, you need this constraint, which says, so if you didn't select the group where item I is contained in, then this is 0, and then the item value has to be 0. So the z variables just say, is the item contained in one of the groups which I selected or not? And you maximize the sum of the weights for this. So this is exactly the projection problem, or the maximum weight coverage problem. And we solved this by exactly by Bennis decomposition. So Bennis, so it's a basic framework. So you divide the problem into a main problem and a sub-problem. So the main problem at the end only has the y variables and this constraint. And you shift out the sub-problem, which are the blue constraints and this objective function. So in the sub-problem, you only have the z variables, and then you do the classical Bennis decomposition approach. So you dualize the sub-problem and generate cuts by the sub-problem for the main problem iteratively. So you iteratively add constraints to the main problem, which are derived by the sub-problem. And yeah, so I will show you in the computations later. We tried this approach, so it can be very hard if there is the number of groups, and if G increases, then it's very hard to solve this problem anyway by Bennis decomposition. So what we were asking ourselves is, can we avoid solving the problem exactly? So it's a hard problem. It's hard to solve. So can we avoid it? And there's a nice solution in the paper of Hector et al. So they have a nice variant of this iterative hard thresholding algorithm, and they go around the exact projection problem, and instead they introduce two approximation problems, the head and the tail approximation. And what you have to do here is, so for the head approximation, you have to maximize over all your G-sparse supports the entry. So you have your given U and you want to maximize the norm of U if you only consider G groups. But you don't have to solve this exactly. You just approximate it by an approximation factor alpha. So your head approximation has to return a vector which is an alpha approximation of this maximum, but the difference to the classical approximation theory in optimization is that the head approximation algorithm can use more groups than we have here. So we consider the maximum here over G groups, but we can use, to approximate this, we can use more groups. We can use G prime groups. And the same for the tail approximation. So here in the head approximation, we maximize what's covered by G groups. Here we minimize what's not covered by G groups. And again, we have an approximation factor beta. And again, this tail approximation can use more groups than we consider here. So if we have these two approximation variants, then they show that if you consider this algorithm, so it's again very similar to the gradient descent, but here you apply the head approximation to the gradient. And afterwards, if you added this to xn, then you apply the tail approximation. And they can also show that if m is large enough, so they have a more general theorem, but this is again applied to the group models. They show it even for general models. But if you apply it to group models, it again says that if you have a number of measurements of, if you have a random Gaussian matrix with the number of measurements is larger than this bound, then this algorithm converges to the true signal X. You have some condition on the approximation factors, but this is true for the classical. If you choose 95% for both, for example, then it's true. So this is actually a nice nice idea to go around the exact projection problem. So now we had to find the head and the tail approximation for the group models. And the head approximation can be done by just a basic greedy algorithm where you always choose the group with the largest total weight. So you sum up all weights in each group and choose the one with the largest weights. And afterwards, when you pick one, so then you delete all weights from the other groups and you iterate. So again, you choose the largest one and so on. And if you do that, and if you go up to G times log E epsilon to the power of -1 groups, so this is the number of groups. So the number of iteration, how often you choose a group, then this easy algorithm gives you a 1 minus epsilon Taylor head approximation. So this can be done in polynomial time. So the head approximation is done. So for the tail, we need the tail approximation. And here we could prove that you can just use LP rounding. So if you assume that every element is contained in at most F groups, so F is called frequency. This is the maximum number of groups in which an element can be. Then you can just use LP rounding. So this is exactly the same problem I showed you before, with the only difference that we have the linear relaxation here. It's not 0, 1 anymore. And you can solve this, then you get a fractional optimal solution Y, and then you just select all groups where this yi variable exceeds some threshold, and you pick all these groups, and you can prove that these groups give you a 1 plus epsilon tail approximation, and the number of these groups is also polynomial. It can be more than G, but yeah, it's still polynomial number of groups. So now we could test both algorithms. So we have, on the one hand, we have the exact version where we have the Bennis decomposition to solve the projection problem. So this is the black and the red line. We always we consider two kinds of groups. So the lower one is with less overlap, and so here the black one is with a lot of overlap. And the pink and the blue line is the approximation variant, where we have this head and tail approximation instead of the exact projection problem. And so what you see here is the runtime. So it seems that the runtime, if you increase n, the dimension of the signal, then the runtime is not very similar to the approximation variant, which is interesting, since you would say, okay, for the yeah, the Bennis decomposition takes much more time. But yeah, you see it if you increase G, then you see this effect. So if with larger G, the Bennis decomposition gets very slow. So in this case, the exact algorithm has much larger runtime, although the number of iterations of the gradient is much less. So if you use the exact projection problem, the number of iterations is smaller, which you would expect. But the Bennis decomposition algorithm is so slow that here the runtime explodes, while the approximation variant for the same groups is very low in runtime. So here it makes definitely sense to use the approximation variant. And one picture I want to show you is so this is the classical compressed sensing picture you often see. So what you want to know is how many measurements do I need to recover my signal. So we have this theoretical bound, which is not really precise. So there are constants involved. So you have to test in practice how much measurements do you need that your algorithm recovers the true signal. So otherwise it diverges sometimes. So it doesn't converge to the true signal. And you see here that there's a point around about 55 to 60% of the dimension. If this is the number of your measurements, then suddenly you can recover your signal. So you have a relative error of 0 here. And you see again here the exact version with the Bennis decomposition for the groups with large overlap needs more measurements. Good. So to summarize, so there's the exact version which can be solved. So the projection problem here can be solved in polynomial time if the tree width is bounded. It's NP-hard if the incidence graph is a grid. And we can solve it by Bennis decomposition in possibly exponential time, but we can use this Bennis decomposition for all groups. So this is here, the groups have a special structure. Here we can use all groups. And then the alternative, which seems to be a good alternative from perspective of runtime, is the approximation variant, where you have this head and tail approximation, which you can solve by greedy and LP rounding. Yeah, and this is all. Thank you very much. For more details, you can check our paper. Thank you.
Okay, thanks, Jannis. Lots of interesting algorithms there. So we can take a few questions. So please feel free to either type it in the chat box or use the raise hand button so we can unmute you and you can ask the question yourself. Okay. There's one from Paulin. Thanks for the talk. What would be an example of the groups and the budget in the image recovery example?
In image recovery, so I have to be honest, I'm not super in the details of the applications, but so if you have wavelet transformation, for example, so if you have a wavelet basis, then so you normally don't show your picture in the classical basis, but you use a wavelet basis, for example. And then your true signal X is the coefficients or the basis, the coefficients you want to have for your to describe your picture in this basis. And for wavelets, I think you can build a tree for these coefficients, and normally for a picture it's that one branch of the tree, if one entry of in one branch is large, then also the other entries in this tree are large. So somehow you have groups, you can group your coefficients into the branches of the tree, for example.
Okay, any other questions?
Yeah, I actually have one. Maybe this is not maybe it's a silly question, but in the algorithm, the model IHT, you have this invariant that each step you have to do the projection because you want to keep it G-sparse, correct?
Yes.
Would there be a way to avoid doing it at every single step and just reducing the number of projection steps in some way by, I don't know, fixing non-G-sparseness every so many iterations and still getting convergence?
Yeah, maybe this could be a good idea. I don't know if the proof for the convergence goes over, but yeah, maybe it. So you have to be sure that you don't diverge in some direction. But yes, sure, could be an idea. Maybe even mixing these two approaches. Yeah.
Right, and actually also with when you were comparing to the approximation results, the G is the input, but the actual like how G-sparse the output is for the approximation, it won't be G-sparse, it'll be something else sparse. So you're plotting the input G there?
Yeah, so the result is what comes out at the end here is G-sparse. It's a very nice result. So in between.
Oh, okay, I missed that then, sorry.
So in between you understood right. So in between what you have here is signals which are not G sparse, but maybe G prime or G prime prime sparse. But at the end, this is part of the theoretical result. It converged to the true G sparse signal.
Got it. And then I guess the last question for me, and then I'll give it back to if anybody else wants to ask, is what if you added noise, like a lot of noise on the signal? How much noise would you be able to handle, and what would you be able to do in that setting?
So I think all the results go through with noise. But there's always, I mean, if you have too much noise, then you don't have any information about your signal anymore. So normally these reconstruction results, if you don't have noise, you reconstruct the true signal with an epsilon error maybe. But if you have noise, then your error has an additional term, which you don't. Yeah. So if the noise is too large, then this also is part of your error at the end.
But you wouldn't change the MIP model in any way to account for the noise?
I think this algorithm goes over with noise. So the MIP model. So if you consider the projected this variant, I think you can use it. And so here the projection problem, the IP methods or the integer methods are only for the projection problem. So here you would not change anything yet.
So I guess part of the answer could be, instead of fx being a squared error, one could have some kind of regularization. But I would imagine that group sparsity is already a way to somehow regularize the space of solutions. So yeah, of course, beyond some threshold, the noise becomes maybe too high that you cannot recover anything with any reliability.
But there are also different approaches, like the group lasso, for example. So this is actually what you say, some regularization, which is based on the group model. So yeah, there are different approaches like this. Yes.
Does anybody else from the audience have any questions?
So I have one. So Jannis, ultimately you reduce the compressed sensing problem, the recovery problem, to a maximum coverage problem. So what would you say about the generality of your method? You know, the algorithms that you propose. Say I have a maximum coverage problem I want to solve. It doesn't come from compressed sensing. Has nothing to do with that. Just comes from some other kind of application. Then a lot of the machinery extends to that, I assume, right? Or can be used directly.
I mean, what we do here is exactly solving the maximum coverage problem. Yeah. So all the IP methods I showed you, you can use for the maximum weight coverage problem.
But perhaps the group sparsity condition is most suitable in compressed sensing, or something like that. Like this is the most suitable application for that kind of assumption, compressed sensing. But there might be others.
I mean, compressed sensing has a lot of other. So you can group model is just one example of model-based compressed sensing. So you can have different structures here. You can the classical version is just having a k-sparse signal, so just k entries are non-equal to 0. So yeah, so this is just one specific structure you can have in your signal, which is good for some applications. Yeah.
Okay, sounds good. Okay, any last questions? If not, then the plan is to do a little social here. So if you'd like to, would like to have you stick around, those who want, you can use that to ask Jannis further questions or just hang out.
Yeah, and we should just say that we are taking a little bit of a summer break after this, but we will be back at some point during for the academic year. We posted a link to a Google form, both in the chat and on our website. And if you can fill that out, we'd like some feedback about the format of dots during the academic year, how often we should have it, how many speakers, and so on. We also, of course, accept feedback on our email and also on the Discord. So yeah, please fill that out and let us know
if people would like to give a talk, there's another form for that.
Yeah, please sign up to give a talk.
Prominent on the website. Yep. Do you want to stop the recording, maybe?
Yep, and now I'll stop recording.